Now we're switching over to problems that have logarithms or equations that have logarithms already in them. So there are two ways to approach this. The way I usually approach it is the inverse method. So one way to approach it is you could just rewrite this logarithm to an exponential like we learned how to do last time. What I'm going to do is called the inverse method, where I exponentiate both sides, because remember, the inverse of a log is an exponential. So the way you exponentiate both sides is you look at the base of the logarithm, and we call it exponentiating because both sides of the equation becomes an exponent. But I use that base of 2. So this is really 2 raised to the log base 2, and then 2 raised to the 5th on the other side. So what that does is it simplifies this side because there's inverses involved. You end up with just 3x minus 4. And then the other side, 2 raised to the 5th power is 32. It just gets rid of that log quickly. And then I just have to go ahead and solve. So I add 4 to both sides. I end up with 3x equals 36. And then I'm going to go ahead and divide both sides by 3. And I'm left with x is equal to 12. Now, before I finish this problem, this won't happen too often, but you can end up with what's called an extraneous solution when you work with logarithms. So you always want to check for extraneous. The easiest, fastest way to do that is to check your argument. So the argument, remember, has to be greater than 0. It can't equal 0. It can't be negative. So our argument in this problem is the 3x minus 4. So we need to make sure that's greater than 0. So I'm just going to plug my answer in and make sure I get a number that is greater than 0, or an expression, or a value that's greater than 0. So 3 times 12 is 36, minus 4 is 32, and 32 is greater than 0, so we know we are good to go. It's not extraneous. Now, this will only happen with logarithm equations that have logarithms in them. You don't have to worry about this with exponentials if the problem starts with an exponential. Okay, let's go ahead and do the next problem. Now, for this problem, I can't exponentiate right away because we've got something after the logarithm, that minus 7. So I need to move that minus 7 over to the other side of the equation to start out this problem. So I'm going to rewrite this. Log base 3, 2x plus 1. And then negative 5 plus 7 is 2. Now that the logarithm is completely isolated, you can go ahead and exponentiate both sides. So the base this time is a 3, so I'm going to do a base of 3. And then remember, each side of the equation becomes an exponent. So 3 raised to the log base 3 of 2x plus 1 simplifies down to just the argument 2x plus 1. And then 3 to the second simplifies down to 9. And then this becomes really easy to solve. So I subtract 1. So 2x equals 8. Divide by 2. And I end up with an answer of x equals 4. Once again, just remember to check, but specifically check the argument. So the argument in this case is 2x plus 1, and we need to make sure that we get a value greater than 0. So I'm going to plug in my answer. So 2 times 4 plus 1. Well, 2 times 4 plus 1 is 9. And 9 is greater than 0, so I know we didn't end up with an extraneous solution. For the most part, you really shouldn't end up with extraneous solutions today, but in future lessons, those will become a lot more common. Okay, let's do another one. So our logarithm is already isolated. So I can go ahead and, exponentiate right away. So I put a base of 3 on both sides of the equation. That simplifies the first half so that we just get x squared minus 5x plus 3. And just as a quick review, remember it's because if you have the same base, they're inverses of each other and they cancel, or they undo each other. So 3 to the second is 9. And then I can go ahead and solve this equation. Now, because I have a quadratic over here, we're going to go ahead and set this equal to 0. And then either factor, or if it doesn't factor, we use the quadratic formula. So we hope it factors so we don't have to go to the quadratic formula. But if it doesn't, quadratic formula works. So I just need to find factors of 6 that subtract to negative 5. Thankfully, we have factors that do. So x minus 6, x plus 1 would be the two factors for this problem. And then remember, you're setting each factor equal to 0. So x minus 6, if we set that equal to 0, you'll get x is equal to positive 6 because you'd add 6 to both sides. And if you set x plus 1 equal to 0, you get x is equal to negative 1 because you would subtract 1 from both sides. So we have two answers. You would have to check both, so let's go ahead and do that. Let's do that over here. So our check. So remember, our argument is x squared minus 5x plus 3, and we need that greater than 0. So, So this would be 6 squared minus 5 times 6 plus 3, and we want that to be greater than 0. So this would be 36 minus 30 plus 3. Well, if you simplify all that, you get 9, which is greater than 0. So 6 works. I'll do a different color for negative 1 just so that we differentiate them. So we're doing negative 1 squared minus 5 times negative 1 plus 3, and we want that greater than 0. Negative 1 squared is 1. Negative 5 times negative 1 is positive 5 plus 3. Well, all of that also adds up to 9, which is greater than 0. So both work. So we keep both answers for this problem. Okay, let's go to another problem. Okay, this one is interesting because if I try to exponentiate right away, I end up with 3 raised to the 2x minus 7, and my variable is suddenly in the exponent. There's actually a simpler way. If you recognize that this piece right here actually simplifies, then you can make this a very, very simple problem. I can tell it simplifies because A, there's no variable, and B, I know that 3 to the second power gives me 9. So log base 3 of 9 simplifies down to 2, because remember we're just looking for the exponent. So I know 2x minus 7 is equal to 2. So I'll solve by adding 7 to both sides. And I have 2x is equal to 9. I divide by 2, and you're left with x is equal to 9 over 2, or 4.5. The other great thing about this problem is the argument is 9, and it has no variable in it, which means there's no possible way for us to have an extraneous solution. So that's just our answer. We're good to go. Okay, let's go ahead to the next one. Just keep moving along. So for this problem, once again, there's a lot of things happening on this side. We have to be able to simplify this for us to be able to solve this problem. So I'm going to look for things I can simplify. And I know I can simplify this one. Number 1, it doesn't have a variable. And number 2, I know 5 to the third power is equal to 125. So this is simplifying. The log base 5 of 125 is just 3 because it's the exponent. So I've got 3 log base 5 of x plus 2 plus the 3 is equal to the 9. So now I can go ahead and simplify and get the log by itself by subtracting 3. So I've got 3 log base 5 of x plus 2, and that is equal to 6. Now the log is still not by itself, so I'm going to divide both sides by 3, I'm going to rewrite that. So log base 5 of x plus 2, 6 divided by 3 is 2. Now, at this point, I can go ahead and exponentiate by doing a base of 5 on both sides. So they're inverses of each other on the left side. Oh, sorry. So we're left with just the argument x plus 2, and then 5 squared is, or 5 to the second is 25. And then last but not least, subtract the 2. Zoom out a little bit, there we go. X is equal to 23. But you always want to check, and you'll notice today it's kind of boring, but I want us to get used to checking every time. The only argument, though, in this problem we have to worry about is the one with the variables, the x plus 2. So we want to make sure x plus 2 is greater than 0. Well, 23 plus 2, that's 25. And we know that's bigger than 0. So we are good to go. Let's go ahead and do another problem. Okay, this one's kind of fun, only because it looks more complicated than it actually is. Now, if you want to, you could exponentiate and do a base of e on both sides. If you do that, you'd get e to the negative x plus 1 equals e to the 5th. And then you'll notice the bases are exactly the same, and you can get rid of it. And I should back up. The reason you would do e is because, remember, e and natural log are actually inverses of each other. But if you recognize that e and natural log are inverses of each other, you don't even have to do that step, because right here we've got an inverse already in the problem. So the natural log and the e undo each other, and you're left with just the exponent, which is negative x plus 1. And that should equal 5. So I'll subtract 1. I've got negative x equals 4. And then if I divide by negative 1, I end up with a result of x equals negative 4. Now, if you check, remember we want e to the negative x plus 1 to be greater than 0. Well, e to the negative 4 plus 1. Well, this would be positive 4 plus 1, or e to the 5th. E to the 5th is going to be a pretty big number, because remember it's about 2.12. Relatively big. It's about 2.7 to the 5th power, which I know is going to be a positive number, but if you need to, just type it into the calculator. I should write down, that's our check. So we are good to go. So like I said, it's kind of boring today on the checks, but next time you're going to see why we really need to check. Okay, last problem, let's do it. This one's fairly easy. It's a log on both sides. If you exponentiate both sides, both sides end up with inverses that undo each other, so you're left with just the argument. So 3x plus 1 equals 121. And then I could subtract 1 from both sides. And then divide by 3. So that one's a pretty easy one. I like it when there's a log on both sides. So I've got x is equal to 40. And I'm just going to do my check up here. So 3 times 40 plus 1. I just want to make sure that's greater than 0. And it is, because you get 121. So I'm good to go.